Hey guys, continuing the VLSI, in this lecture we are going to talk about VLSI chip types and ideal switches and Boolean operations. So what exactly are these VLSI chip types? There are three major types of VLSI chips. The first is full custom design. Full custom design, it's like every circuit is custom designed for the project. Now this task is extremely tedious and time consuming process. Also, since these circuits are specific for a particular application, you cannot use it somewhere else. Example, let's say you are making a chip for separately for Dell computers, then you are making a separate processor for Lenovo, you are making separate processor for MacBooks. So now it's a very heavy task for Intel to make processors which are way different for each of the computers with required number of specifications with each of the, let's say, model numbers. Okay, that's too huge and that's totally absurd. But sometimes you actually require such designs where you know that a specific chip is required, otherwise the work will not get completed. That is full custom design. Then there comes application specific integrated circuit, that is also known as ASICs. Now these ASIC ICs are like for particular application. For example, let's say you just want something which only adds, or something which only subtracts, or something which only multiplies two numbers. So what you can do, that you can have ASICs. How useful are ASICs is because let's say you want to make a calculator, in that you want to have a chip which adds just two numbers, something which just subtracts, then multiplies, and then divides. So you can have four different chips, each performing a specific task. Okay, that, and then you can integrate them on a chip. So these are very popular for low volume production, because such types of calculators, if you want to produce in low volume so that the students of your university, of your class, can use it, so it is very useful. Also for prototyping it's very good, but for large mass production, for making it available for everyone, the ASICs are not so good. Also, these are designed using CAD tools. CADs are nothing but computer aided design. Okay, these are software tools which you can use. Some of the popular are ngSpice, pSpice, LTSpice. Okay, these are some popular programs that can be used for designing. Now the drawback of ASIC is that the characteristics, such as let's say speed of how fast your transistors are switching and everything is happening, this is set by the architectural design. Okay, these are predefined in ngSpice or pSpice. You cannot change it, so the designer does not have access to the electronics. Okay, so basically what I'm saying is, let's say you want to improve the design, you want to reduce the size of transistor, you want to reduce the size of silicon wafer, that cannot be done in ASICs because these are predefined. There's no way you can change it. You can just use what the tools you have and then design something new. Let's say in the recent coming trends, the ASICs have grown to be more useful, more sophisticated, and the designs are nearly as same or as similar as those available in the market. Then comes a middle ground, okay, which is semi-custom design. So as the name suggests, it is semi-custom. That is it is in between full custom and ASICs. Now the majority of chips are designed using a group of primitive predefined cells, and each cell provides a basic function such as a logic operation or a storage circuit. Okay, so basically what I'm saying is that there are cells and each cell has a specific operation, and the master design, it resides in a database collection which is also known as library. Now if suppose The problem with ASIC, as you all remember, is that the designer does not have access to the electronics, but in semi-custom design, the designer has the option to create a custom library, to create a custom design, upload it to the software, and then use his or her own custom design to make the product. So these were the VLSI chip types. Then next comes ideal switches and Boolean operations. Now know one thing, MOSFETs, as I have seen, is like when it is taught, teachers basically directly jump into showing MOSFETs and how it is used to make gates and everything. And it actually gives a fear of VLSI. But comparatively, VLSI is an easy topic to understand if you go it like a step by step. I can say that our knowledge is somewhere here. Below it comes those MOSFETs or the level, okay? Below it, in the sense, the level. We are on our middle ground, and below this ground, as you go in depth, you come across CMOS, NMOS, PMOS and all those stuffs. And when you go up, you come across stuffs like integration on a single chip, and then like production and everything, CAD tools. So I think this is the best ground that we have, and this is something which we have been studying right from 5th or 6th standard. The most basic example that can be used to know VLSI is switches. The switches, the normal switches that you have in your homes for switching a fan on and off, we can use those examples to understand and to give the ground for our VLSI technology and our VLSI design and CMOS and NMOS. So let's get started. Please know that logic gates are the basic building blocks in a complex switching networks in VLSI. And these logic gates are actually made by controlled switches. If you remember my previous video, I told that transistors were the part of logic gates, but transistors are nothing but they transfer resistance. They are basically on and off switch. So we'll take a switch. Okay, I will say that logic gates are nothing but made of switches. And in ideal situation, the state of this switch is determined by a control variable A. Let's call that variable A. Now, if you know, if you have seen, and I am very sure that you have, that when this switch is above the contacts, it is basically open or the circuit is off. I can say that this variable A is equal to 0. That is, there is no connection between the input X and output Y. But when this switch is pushed down, okay, I am pushing it down, then it makes a contact between the input and output, and this circuit gets completed. So what will happen is this X will travel all the way through this wire via the switch to the other wire to the output. I can say that my output Y with previous output Y is now equal to the input X. So that is why I have written as Y equals to X. Also at this time, my control variable or the state of this switch is 1. That is, my A is equal to 1. I can write this equation in a better format, that is Y equal to X into A if and only if A equals to 1. So what will now happen is that Y will be equal to X into, when X A is equal to 1, it is equal to X into 1, that is X. So Y equals to X, and that is what we saw here, right? Yes. Now let's move forward. This was a basic on and off switch, or open and close switch. If I talk about series connection of these switches, basically I have two switches, A and B. Okay, the input is 1. Now if I push this switch down, what will happen is this A will make a contact here, and 1 multiplied by a. Why am I multiplying? Because previously I saw that x was multiplied by this control variable a, and that is why I got x into a. So in the similar manner, 1 multiplied by a will give me a into 1. This was when the first contact was made, okay, when a switch was pressed down or it is closed. And now if I forget about this, I have input as a into 1 and this b switch is pressed down or it is closed. So basically I will have a into 1 multiplied by b. That's what I have written. So this output G, final output G, will be equal to a into 1 is nothing but a multiplied by b will give me a dot b. Now if I want this output a into b, I have to simultaneously close both of these switches. If any one of the switch is not closed, if any one of the switch is open, let's say this switch is open, the input will not travel here. Okay, there will be no input here, nothing will be present here, and nothing will be multiplied by b, and I won't get an output. The same applies to this case. If b is open, okay, then that means there is no connection. A into 1 will be here, but there will be no connection between a into 1 and this output G. So I have to simultaneously press both of these switches down, which means I am ANDing them. ANDing in the sense A and B have to be pressed simultaneously, then and only then an output will be received. So notice that AND operation is nothing but a multiplication between the inputs. Now let's talk about parallel connection. In parallel connection, I have input 1 and I have two switches A and B which are parallel to each other. Now if A is closed, I will have 1 multiplied by A, which is nothing but A into 1. If B is closed, then I will have 1 multiplied by B, that which is nothing but B into 1. Now output will be nothing but a addition of both of these. Why addition? Why not multiplication as in the previous one? Because logically, if this switch is off but this switch is on, the current will flow from here and it will pass through this wire and it will reach output. If this switch is open and this switch is closed, okay, the current will move from here and reach the output. So basically, if any one of the switches is on, or I can say any one of the switches is closed, the input will travel all the way to the output. So either this or this needs to be pressed, or this needs to be closed. That is why a OR operation is used, and this will give me A into 1 is nothing but A, or B into 1 is nothing but B. So basically I can have both of the switches closed or any one of the switches closed, and still I will have an output. Now these type of switches are called as Assert high switch. Please note this name, Assert high. Okay. Assert high switches are the normal switches that we just saw. Then obviously there is a alter ego for Assert high, which is known as Assert low switch. It behaves exactly opposite to what we just saw. So we saw that when this is represented by a bubble, okay, I have differentiated between this Assert low switch and Assert high switch by a bubble. There's a bubble present here, and in Assert high switches there was no bubble here. Okay, now previously we saw that when this was closed we had output, but in Assert low, when the switch is closed there will be no output, but when the switch is open there will be output, that is X will reach Y. So I can say that Y equals to X into A bar if and only if A equals to 0, because If I solve this, I will have y is equal to x into a bar means 0 bar because a is equal to 0. And when a is equal to 0, so 0 bar will give me 1. So that means x into 1, which is nothing but x. So y equals to x if and only if a is equal to 0. Now let's talk about series connected complementary switches. So here I will have a bar, b bar, and when they are closed there will be no output. Sorry, when they are open there will be no output because I have a bar here. But when they are closed, I will have 1 into a bar, which will give me a bar into 1, and then a bar into 1 multiplied by b bar will give me a bar into 1 multiplied by b bar, and in the output I will have a bar multiplied by b bar. Okay, please specifically note this is a bar and not a, so these switches need to be closed for the output, for the input to travel to output. Okay, so by De Morgan's law, a bar into b bar is nothing but a bar, a plus b, the whole bar. This is just a De Morgan's relation, and using this relation, I can say that a similar relation will be obtained for parallel connected switches. Now what if I use both type of switches, that is assert high and assert low in one single circuit? So by using assert high and assert low in a single circuit, I will have a NOT gate. Okay, so this is assert low switch, this is assert high switch, and we are using two inputs, 1 and 0. So 1 if travels from here, this is a bubble, and since this is a, so I need to like pull it up for the output to travel, or I have to like push it down and have a bar here. So 1 multiplied by a bar will give me a bar into 1, and here if this is, it has to be pushed down. 0 multiplied by a will give me a into 0, and now my output is nothing but a bar into 1, which is nothing but a bar. And since this is an OR operation, why? Because these are parallel. So plus a into 0 is nothing but 0, so y will be equal to a bar. Now y equals to a bar is nothing but a NOT operation. This is nothing but a NOT gate. So basically by using two types of switches, assert high and assert low switch, I can create a NOT gate. Why did we go into so much of switches? Reason being, MOSFET is nothing but a switch. Okay, if you understand these concepts very well of bubbled assert low switch and non-bubbled assert high switch, you will have no difficulty in making circuits, making NOT gates using MOSFETs. Let me tell you, a NFET or NMOS, okay, basically NMOS or NFET as it is also known as, looks something like this, and this is NMOS, and a PMOS looks something like this. Okay, so this is nothing but similar to assert high switch without any bubbles, and this is nothing but similar to assert low switch with bubbles, and by using both of these you can create a NOT gate. Similar manner, okay, you just have to place this here, place this here, connect it, and you will have a NOT gate. Okay, and in upcoming lectures you will be taught how to connect them, what are the problems that we face, and how good are NMOS, PMOS combined. Okay, why not only NMOS, why not only PMOS, but a combination of both which gives us CMOS is very good. Thank you so much.